Hey everybody in Honors Pre-Calc. Today we're going to be starting lesson 6.1. Welcome to Unit 6. This unit is all about using trig identities. So this is our last major trig unit. And what we're going to be doing today is using fundamental trig identities. So the first few that we're going to learn. And you're going to need to use those to factor and verify some trig expressions. The essential question today is how do you apply fundamental trig identities? Of course, we already know a lot about trig functions. And here's an example of a question you'll be able to solve at the end of today's lesson. So if I gave you sine of t plus cotangent of t times cosine of t, simplify it so that it is only one term containing one trig function. Okay, so I'm going to switch over to the notes and I'll tell you a little bit more about what this means. So here are our notes for today, but before we even look at the notes, I wanted to show you this formula sheet. So this is our chapter 6 formula sheet. It has all of the trig identities is what they're called that we're going to be using throughout the unit. It's a whole bunch of formulas, and don't worry, you're not going to have to memorize these. But today, what we consider to be the fundamental identities are the top 3 sections. So today we're going to be talking about reciprocal identities, quotient identities, and Pythagorean identities. The reciprocal identities, we really already know, right? Think of, all of these use u and sometimes v instead of like theta, but we know that sine is equal to 1 over cosecant. Cosecant is equal to 1 over sine. We know these already. We've used these quotient identities before, you might not remember, but we've used these before as well, right? Sine over cosine equals tangent. That makes sense if you think that sine is the y value of an ordered pair, cosine is the x value of an ordered pair, tangent is y over x. So it makes sense that sine over cosine would equal tangent. The same is true if we flip sine over cosine and we flip tangent, we're going to get cotangent, okay? Pythagorean identities are a little bit more work. We're not going to go through proofs to show you why these are true. We're just going to accept that they are, but it does have to do with right triangles, right, and the Pythagorean theorem. But sine squared plus cosine squared equals 1, 1 plus tangent squared equals secant squared, and 1 plus cotangent squared equals cosecant squared. All right, you'll see some of each of those today at some point. And this connects to the previous activity that you did. So in the previous activity, you rearranged dominoes to make a path from a starting point to a finish point. And I want you to think about that while we're going through the lesson today. Think of these identities as like your dominoes to get you from some point to the next point. And what we have to do is figure out which ones do we need to use and what order do they need to go in order to actually help us solve a problem, okay? It's going to be fairly similar to when you use, when you did proofs in geometry. However, you don't have to do 2-column proofs. You don't have to write out a reason why you're doing each step. And in my opinion, I think from what I've seen that students usually have a better time with this, even if they may have struggled with proofs in geometry. So if you love proofs, then you're going to love this. We'll see how it goes. Okay, so let's take a look at the first example. Simplifying a trig expression. So we're going to start with sine of x times cosine squared of x minus sine of x. And we are not interested in what this graph looks like. We're not interested in the amplitude, the phase shift, anything like that. I don't want to know how this relates to triangles or even circles, right? Our only goal here in this unit is going to be using identities to accomplish goals given in the question. It's the same trig functions. They mean the same things. We're just adapting it, looking at it in a different way, okay? We will have to use the unit circle a little bit in this unit, but I don't think that we will need it today. So we're going to try to simplify this expression. It should only be one term containing only one trig function. So think about this as like our starting point. Our ending point is just a description, and we're going to try to use our quote dominoes to get from point A to point B. So the first thing I'm going to do is not technically a domino from our formula sheet. I'm just going to factor out sine of x because I can see that's in both of the terms here. So if I pull out sine of x, I'm going to be left with cosine squared x minus 1. Now don't forget that exponent of 2 right there, that's just a fancy way of saying cosine x but squared. And I'm going to put an aside over here to show you that. Cosine squared x means the cosine x is what's squared. The reason we write it like that is because if you saw this, it is not great notation because we don't know if the x is what's squared within the cosine or if the cosine x is squared. I would probably assume that that would mean that the x is squared within the cosine, which is something totally different from the whole cosine of x being squared. So we are going to most commonly see the exponent be written right after cosine, but before the x, depending on the trig function. So now we have cosine squared x minus 1. We're trying to make only one term and only one type of trig function. And right now, we still have too much stuff going on. So I'm going to go over to my formula sheet. We're going to be looking at the Pythagorean identities, specifically the first one here. I'm going to do a secondary aside here and write that one down. So it's sine squared u plus cosine squared u equals 1. And the reason my eyes were drawn to that identity is because I have cosine squared and I have a 1. And wouldn't it be nice if that was what this looked like? So what I'm going to do is show you that we can, with a couple steps, we can manipulate this identity so that's something that we can use over here. So if I subtract the 1 over to the left, you can see now we have what we're looking for right there. So now I'm going to subtract the sine squared to the other side. And this identity gives me a formula that I can use to replace this. So now this is kind of like our domino that's going to take us to our next step. So this we're going to replace with negative sine squared. And since x is in place of u, I'm going to write an x as I write a u. I'm going to write an x there. My hand was probably covering it anyway, so you probably couldn't see it in the camera, but that's an x. So it's sine x times negative sine squared of x. And this can multiply. If we have 1 sine x multiplied by sine squared, it's going to become negative sine cubed of x. And now we have one term, and it's containing only one type of trig function, right? Sine. So we did it. So normally, in a normal question, we wouldn't have to write out all these steps showing the identity being kind of maneuvered around. And the more that we do this, you're going to be able to kind of see this in your head. You definitely don't have to write this in every question. That was just there to kind of show us the notation of the exponent. But anyway, let's keep going. Example 2, factoring a trig expression. Factoring is often a part of other fundamental or verification or solving problems that we're going to be doing this unit. So like you can see up here, we had to factor out a sine x. We're going to try some more complex factoring with trig functions in this next example. So let's take a look at letter A. We have secant squared of theta minus 1. There's not necessarily only one variable we're going to be seeing this unit. So in this question, you can already see there's a theta and there's an x. On the formula sheet, it's u. Just depends on the question, but we want to be consistent with the variable that's given in the question. So when you get to calculus, there's going to be this thing called u substitution. And I wanted to show you a preview of it now so that you know kind of what it means. And this is going to help us to be able to see the factoring that is actually possible in these questions, even if we can't see it yet. So what I'm going to do first is I am going to let u equal secant of theta in this first question. And whenever I'm in u substitution mode, I'm going to switch colors so that it becomes obvious what's going on. So if I was going to rewrite this expression, but with u in replacing every secant of theta, remember the secant of theta here is what's squared. So it's going to become u squared minus 1. And that is a difference of squares pattern, which means it factors to u plus 1 times u minus 1. If you didn't remember that, I can write that up here. We know a squared minus b squared equals a plus b times a minus b. That's a difference of two squares. And this could have been factored originally when it's in this format, secant squared of theta minus 1. But, I mean, we've never seen it written like that before. So now that we switched it to U substitution, I think the factoring kind of popped out at us a little bit easier. And now our last step is going to be to switch back to secant of theta. We don't want our final answer to have U in it because that's not how the original question was given. So we're going to end up with secant of theta plus 1 times secant of theta minus 1. All right, I'm going to do the same thing in the next question. This time I'm going to let U equal tangent of theta. So I am going to go through and change everything to U. So it'll become 4U squared plus U minus 3. And now this looks like a quadratic that we can factor. And indeed it does factor. Whatever factoring method you want to use to factor this, please do. But once you use some sort of factoring method, you're going to end up with 4U minus 3 and U plus 1. And if we switch back out of the U substitution, plug back in tangent, we're going to end up with the factored form that is 4 tangent of theta minus 3 times tangent of theta plus 1. All right, let's take a look at letter C. Now, in letter C, I have an issue, and the issue is that we have cosecant and cotangent, so no U substitution is going to make these into the same thing. So let's take a look back at our formula sheet. We're going to look at the Pythagorean identities, and this time we're going to look at the third Pythagorean identity. It says 1 plus cotangent squared equals cosecant squared. That's great news, because I can replace cosecant squared with 1 plus cotangent squared, and I have another cotangent. So that's what I'm going to be replacing with 1 plus cotangent squared. And I'm going to rearrange this so that it is written more properly and the like terms are combined. So I'm going to end up with cotangent squared x minus cotangent x negative 3 plus 1 is going to be negative 2. Now it's time for the U substitution. So we're going to let U equal cotangent x. So I'm going to get U squared minus U minus 2. That factors to U minus 2, U plus 1. Let me just check that. I'll get U squared plus 1 minus 2 minus 2. Yep. And then we're ready to switch back to cotangents. So we'll get cotangent of x minus 2 times cotangent of x plus 1. There we go. We factored successfully. Now again, if you can see this, and you don't have to think about U substitution to get there, you don't have to use the U substitution here. There are questions once you get to calculus where you will have to use some form of U substitution in order to answer the question, but that's not how it is right now. So don't worry too much about that if you don't need it. But there you go. That is how we factor. Let's take a look at example 3. We're going to simplify sine of t plus cotangent of t plus cosine of t, not plus, cotangent of t times cosine of t, so that it is one term containing only one trig function, similar to example 1. So let's see. This is the first of many questions where we're going to have to come up with some strategies to solve. So I'm going to make a note on the side here to tell you that pretty common strategy is to try to change every trig function into sines and cosines. Try changing all trig functions into sine and cosine. That's going to be helpful because if everything's a sine and cosine, then we'll be able to cancel some things out. There's easy ways to change everything into sine and cosine using our identities, right? Because sine and cosine are already sine and cosine. Cosecant and secant can become 1 over sine or 1 over cosine, respectively. And tangent is sine over cosine, cotangent is cosine over sine. So if we do that, we'll see if anything cancels out. So let's try it. So we start, and this is how I typically write out these types of questions where we're simplifying or verifying something. I'll start with the original question. And this question is weird because it has plus and it has t's. I'll try to make my t's look curved so they look different than my plus signs, but that's just me personally. In this question, we already have a sine, we already have a cosine, so let's change the cotangent to cosine over sine. So our second step, which I usually write down for the steps in this type of question, and we'll get sine of t plus cotangent, which is, again, cosine t over sine t times cosine t. And nothing immediately canceled out, but I'm going to rewrite this now. Multiply together. So the cosine times the cosine gives me cosine squared t over sine of t. Okay. So another strategy is to try to find a common denominator if we have multiple terms. Let's write that out too. Strategy number 2. We write out when there are multiple terms, consider finding a common denominator. Okay, so let's try that. In this question, now we have a denominator of sine of t for this right term. So for the left term, what we're going to do is we're going to multiply by sine of t over sine of t. I'll write that in red so that it's clear that it wasn't originally part of that step, but I'm going to end up with sine squared of t over sine of t plus cosine squared of t over sine t. Another reason that I wanted to consider doing that is because this is supposed to end up as one term. So somehow these are going to combine. Might as well try to find a common denominator so that they can combine a little bit easier. So now we have our common denominator, so the numerators can add. And the denominator stays the same. And one more trick over to our formula sheet for identities. You may recognize the numerator from earlier, sine squared plus cosine squared just equals 1. So the next step is just 1 over sine of t. We don't have to write that we use the Pythagorean identity. We just write it. And as long as you're clear with what comes after what, and you only do one thing at a time, then it's going to be clear to the reader, most likely me, what you mean, okay? So now we have 1 over sine, and we're going to do one more step. 1 over sine equals cosecant. So our last step is going to be that this really simplified to cosecant of t, which is wild if you graph sine of t plus cotangent of t times cosine of t, and then you graph cosecant of t. The graphs are going to look exactly the same. And those are the steps, okay? We've got a couple more questions, a couple more verifying questions on the back. So let's keep going. Example 4. Verify a trig identity. Verify that sine of theta over 1 plus cosine of theta plus cosine of theta over sine of theta equals cosecant of theta. So now we're given the starting step. We're giving the last step. Think again about our dominoes. We're going to use our identities, the formulas, as like the dominoes to fill in all the missing steps in between to get from the beginning to the end. So I'm going to write out the first step under here, the starting point. All right, so let's think about the strategies that we know so far. We know that it might be helpful if we change everything into sines and cosines. Okay, well, that's already done here. Our second strategy was consider finding a common denominator if you have multiple terms. And in this question, we start with 2 terms. We know we're going to have to end with 1 term. So it's actually a pretty good idea to try to find a common denominator. So what we're going to do here is my 2 different denominators are 1 plus cosine and sine. So I'm going to multiply this fraction by 1 plus cosine theta over 1 plus cosine theta. I'm going to multiply this fraction by sine over sine. And I'm going to leave the denominator factored and multiply the numerators. So sine times sine is sine squared over sine of theta times 1 plus cosine theta. On the right side, if I distribute the multiplication here, we end up with cosine theta plus cosine squared theta over, and again, I'm going to leave the denominator factored. That's a pretty common strategy as well. You'll still see why in a little bit. And now we have the common denominator. So we can combine the numerators. We end up with sine squared theta plus cosine theta plus cosine squared theta. Those can't combine because it's plus and they have different amounts of cosine thetas. The bottom stays the same, sine of theta times 1 plus cosine theta. And I'm going to move up to my next line here. And on top, hidden in here, I have sine squared plus cosine squared. And we just looked at that formula, saw that that really equals 1. So I have 1 hidden up here. So this is really 1 plus cosine theta, right? There's still an extra cosine theta in there. So the sine squared plus the cosine squared equals 1. The cosine stays there. And on the bottom, I have still the same thing. But maybe you're seeing where we're headed here. The 1 plus cosine on top and this 1 plus cosine on the bottom can cancel out. So we're just left with 1 over sine of theta. And 1 over sine of theta equals cosecant. So this now equals just cosecant of theta. This question said to verify, we were given the starting point, we were given the ending point. We had successfully got to the finish line. So I like to put a little check after I box the answer. We say, check, verified. We did it. Okay. All right, let's keep going. Example 5, rewrite a trig expression. Rewrite 1 over 1 plus sine of x so that it is not in fractional form using conjugate pairs. So conjugate pairs work the same with trig as they did with square roots and any other time with imaginary numbers that we've used them this year. So we are going to multiply by 1 minus sine of x. So it always means the sign in the middle switches, everything else stays the same. So we're going to start with 1 over 1 plus sine of x. And we're going to multiply by 1 minus sine x over 1 minus sine x. And on top, that just means we're going to get 1 minus sine x. On the bottom, let's think about foiling this. So we're going to get 1. For the outer, we'll get minus sine x. For the inner, we'll get plus sine x. So those canceled out. And the last is going to be minus sine x squared, which of course I write as sine squared x. And let's see, we don't want this to be a fraction anymore. It's still a fraction. 1 minus sine squared is really making me think, that looks a lot like a Pythagorean identity. And that identity has 1 in it and it has sine squared in it. If we subtract this sine squared to the other sides in our mind, then this side would be 1 minus sine squared and it would equal cosine squared. So because of that, I can change the denominator to cosine squared. Okay. And then let's see, what next? We don't want this to be fraction anymore. I think it might work out okay if we separate the numerator into 2 different fractions. So we're going to get 1 over cosine squared x minus sine x over cosine squared x. And I did that because 1 over cosine is secant. So that's a good sign. We can get rid of the fraction. Now that had a cosine squared in it. So 1 over cosine squared is going to equal secant squared. You can change any of these reciprocal or quotient identities to squared and they do the same thing. You just have to kind of filter through the squares, make sure the squares are everywhere. Pythagorean identities don't work like that. Sine plus cosine doesn't equal 1. And it has to be sine squared plus cosine squared. But up here, you can add in exponents and the properties work the same way. So 1 over cosine squared is going to equal secant squared. So this now could be secant squared x minus sine x over, and I'm just going to say that cosine squared equals cosine x times cosine x. And there's a reason that I wanted to do that, which is just another way of writing the same thing. And that's because I am going to kind of lump the sine in with one of the cosines from the denominator to create, ding, 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 a tangent. So let's rewrite this one more time before we actually officially do that. We're going to end up with secant squared x minus sine x over cosine x times 1 over cosine x. So I just kind of factored out one of the cosines, made it into its own fraction. And now this can be secant squared x minus sine over cosine, which I just said was tangent, and 1 over cosine, which again, if we look over here, is secant. And we officially made no more fractions. So we got it. Again, crazy that 1 over 1 plus sine of x and secant squared x minus tangent x times secant x are the same. They would have the same graph. It's crazy, okay? But it's true. One more question, example 6, trig substitution. Use the substitution x equals 2 tangent of theta to express the square root of 4 plus x squared as a trig function of theta. In parentheses, this question is a fancy way of saying substitute x into the expression and simplify. So that's what we're going to do. We're going to take square root of 4 plus x squared and plug in 2 tangent of theta where the x was. So if we start with 4 plus x squared in the square root, we could rewrite to 4 plus 2 tangent of theta squared. And we need to make sure that we distribute the squared to everything that was in there. So it's 4 plus 4 tangent squared of theta. And we're going to try to simplify this so that there is no more square root. So the next step may not be initially obvious, but after we do it this one time, then you should be a pro. You can look back at this question, of course, when you try the one that's in the homework. We can factor out a 4, and we're left with 1 plus tangent squared of theta. That is great news because 1 plus tangent squared equals secant squared. So we can replace that with 4 secant squared of theta. So the 1 plus tangent squared all went away and became secant squared. And now we have a square root of one term, and both of the parts of that term are perfect squares. So the 4 becomes a 2, the secant squared becomes a secant, and we have officially simplified to 2 secant of theta. All right, so that is the last question. I know that this lesson and this idea and using all these formulas is brand new, and you're not necessarily a pro at this yet. You will become a pro. So when you're doing the homework, I included an answer key that has a lot of the work on it so that you can check as you go. If you get stuck, you can see the steps. I really, really encourage you to try the whole homework before you look at the answer key. Obviously, don't just copy the answer key because that's going to come back to bite you when we have to perform this for any sort of assessment, right? So try your hardest. Let me know if you have any questions, and don't get frustrated, okay? Have a fantastic day. Thanks for watching.